然后把这个。
We're just going to go ahead and give everyone just a little bit longer to come on in. So just be patient for, please be patient for a little bit longer.
Yeah, we all kind of have our own colors. And then
All right, let's go ahead and get started. I'll just start my screen share. And we should be able to, all right. So before we get things started, I just wanted to spend a little bit of time talking about just like a quick self-introduction, right? Let you guys know a little bit about me, and then talk about what we plan on going through, as well as a couple of the ways that I plan on doing this class, right? So for the most of you, I'm pretty sure this is your first time taking a class with me. So I want to take a little bit of time and just kind of explain how things are going to go. So my name is Kitong Liu. You guys can call me Mr. Liu, Teacher Liu, anything you want, really. So I graduated from the University of Texas at Austin with a math degree. I currently work in insurance pricing, so I use a lot of math there. So this is going to be the Algebra 1 class. We're going to go over the materials in the Art of Problem Solving textbook. We can see here Chapter 1, follow the rules. This is really just a lot of review here. Chapter 2 starts introducing x, and we start using it a lot more. Then we're going to move on into variable equations, using more variables, multivariable linear equations, ratios and percents, proportions. These two are typically get paired together quite a bit. Then we're going to show a little bit of graphing, inequalities, and from there we're going to move on into quadratics, special factorizations. We're going to introduce complex numbers, move on into some more quadratic equations, graph those quadratics, more inequalities, and then functions, graphing functions, polynomials, some exponents, and then from there we're going to end up just wrapping things off with special functions, sequences, and just a little bit of manipulation. So this is just kind of an overall idea of what we're going to go through. Can anyone else hear me? Just say something in the chat if you can, or go ahead and unmute if you can hear me. Okay, yeah, everyone else should be able to hear me. If you're not able to hear me, just go ahead and I think they may have already left and tried to rejoin. But right, like if at any time you're unable to hear me, just go ahead and leave and then come back, and that should fix the issue. Yeah. All right. Can you hear me now? Is everything good?
Yeah, I can hear you now.
Okay, good. All right. And yeah, so all of our classes are going to be, they're all going to be recorded. They're all going to be posted. So if you have to watch a replay of something, you'll be able to find that there. And lastly, as for the way that I want to do this class, I don't think webcams are a good idea. I think like they can tend to be very distracting, especially when I'm sharing something on screen, right? So I want you all to pay attention to I want you to pay attention to what I am drawing and what I'm showing on screen, rather than looking at like a webcam or something like that, right? So that's going to be the way that I want to do things. And as for, if you have any questions, if you feel like I'm speaking too quickly, anything like that, just please say so either in the chat or go ahead and unmute and ask a question. If I see that you've unmuted, I'm going to assume that you're wanting to ask a question. So please don't unmute unless like one of two things. You're answering a question that I ask, or and I will ask a lot, or you are trying to ask a question of your own. And if you and I'm typically going to go down the list one by one and just ask people questions one by one, and then when I do that, you can either go ahead and unmute and answer, or you can answer by using the chat box. I'm okay with either, or I'm always looking at the chat, so I am always I should be able to see. But if you plan on answering using the chat, please say please just use something there first, so I know to expect it there, instead of just sitting around and maybe not knowing whether or not you're actually here. Because like maybe you went off to do something, which is, I mean, totally fine, right? But with that being said, let's go ahead and get things started. So the algebra book starts off by really explaining, by starting off by taking a little bit of arithmetic in, right? Because we all need to start from somewhere, right? So we're all familiar with the regular operations: addition, multiplication, subtraction, and division, right? And at this point, we should be somewhat familiar with using variables, right? We can pick letters that will stand for numbers. Say, for example, if we originally have something of the sort like 2 plus 4 equals 6, but let's say we don't know what the numbers on the left side are. Let's say we don't know it's necessarily 2 or 4. We just know that they add up to 6. We just know that we have two numbers that add up to 6. Well, these two numbers aren't necessarily the same, so we might need to make them different, right? So if we have, say, for example, a plus b, those could represent two separate numbers, and then this would then equal 6. If we wanted to, this doesn't necessarily have to be a and b. It could have been x and y. It could have been L and M. It could have been literally any two variables. It could have been a box and a triangle for all we cared. As long as it represents that it is a number, we should be fine here. So yeah, this is just a general rule of thumb. This is really what we base a lot of algebra off of. The fact that we have variables that stand in for numbers. This is going to be the key idea that you're going to see many, many, many times from here on out. It's actually going to be the big concept that makes a lot of math work from here on out, right? So if we want to move on, we also need to talk about numbers. We need to talk about what important numbers there are, right? So the basics are we have what we call whole numbers. We have integers. So does anyone actually know what the difference between whole numbers and integers are? Anyone? So a whole number starts from 0, then we count 1, 2, 3, 4, so on and so forth, right? These are going to be our whole numbers. They are pretty much the numbers that we can typically think of, while integers are these numbers in addition to their negative counterparts. So we'll have, for example, -4, -3, -2, 0, 1, 2, and so on and so forth. So we're going to have all of those negative numbers and those positive numbers. Those are going to be what we call integers, okay? So actually, let's keep these up for now. Maybe we can change these numbers a little bit to just be starting from -2. But integers does include 0. All right. So moving from here, we then have what we call rational numbers. These are going to be one integer divided by another. As long as we can represent it as one integer divided by another, this is a rational number. So integer divided by integer. For example, 1/3 is a rational number. 4/7 is a rational number. And 1 itself is also a rational number, right? Because 1 is just 1/1, right? So all of your integers are rational numbers. All of your whole numbers are integers, and so on and so forth. And lastly, we have what we call, well, not really lastly, but for now, we have what we call real numbers. Real numbers are going to be numbers that are including these rational numbers. We can write them as a decimal, even if we have to use an infinite amount of those decimal places. So examples of real numbers that are not rational would be, for example, the square root of 2, pi, and even this little character that we like to call e. This one, many of you may not have heard of before, but this is around equal to 2.718 or so. But all right.
Oh man.
Okay. So with that being said, these are just going to be the types of numbers that we're going to be working with here. Starting off, we're going to really work with just integers for a good while. And then we're going to start moving into rational numbers and real numbers slowly from there. We are going to introduce that there are more numbers than this. We're specifically, we're going to start talking about numbers that are not real at all. And I will say one last thing, that all rational numbers are real, all integers are rational, and all whole numbers are integers. So that means as well that all integers are real and all whole numbers are real, as well as all whole numbers are rational numbers as well. All right. Any questions here? Okay. So moving on, the next section talks about order of operations. So there's different ways that I've seen order of operations expressed. The one that we used to teach was always just PEMDAS, but it's possible that you've seen, it's possible that you've been taught GEMS instead. I was told that by someone else, but either way, if you see PEMDAS, that is going to be PEMDAS, where P stands for parentheses, E stands for exponents, M stands for multiplication, division, addition, and subtraction. But if you see GEMS instead, this is effectively the same thing, where G stands for grouping instead. E stands for exponents, M stands for multiplication, and S stands for subtraction. Now, the thing about this is you may notice that we don't have addition or division listed here. The reason why is because multiplication and division are actually the same thing. They're one and the same, as well as addition and subtraction. They're the exact same thing. And then parentheses is the same thing as just grouping. So the reason why we only listed a single time here instead of twice is because we're basically just saying these two things, they're pretty much the same thing. So we only list a single time instead. And the reason why it's the same thing is a concept that is brought up in pre-algebra. Because subtraction is just the addition of a negative number, right? Like think about, say for example, 10 minus 4, this is the same thing as 10 plus negative 4, right? So this is just the same exact thing. Subtraction is just the same exact thing as addition. And then if you're multiplying and dividing instead, say for example, 9 divided by 3, this is the same thing as 9 times 1/3, right? So, and then from this idea as well, multiplication is just the exact same thing as division. Okay. All right, so now that we've talked about the order of operations, there's just one thing that we need to make sure that we don't do, and that is division by 0. Division by 0 never works. You're told to say that if you ever do have to do it, it's just going to give you an undefined result. So we're not going to, if you do see division by 0, just your answer there does not exist. Okay, so let's take a look at a couple of problems. Leave this one right here. Question 1.1. We want to evaluate each of these following problems. Okay, so let's see. Let's just go down the list. So first up, I see student 211, Lin Zeban, is that right? I'm not sure. Let me know if I pronounced it incorrectly. We'll just go into the next one then. Student 313, Yang. Oh, okay.
Yeah, I'm here.
What's your name? Sorry.
My name is Yang Xiaowen.
Yang. What was the second one? Sorry. Second.
Yang
character?
Xiaowen.
Doll. Is that right?
Xiao.
Okay. Sorry. Can you type out the peen?
Wait, what'd you say?
Can you type out the peen for your second character here?
Where?
Just in the chat. Sorry, I'm just
Uh,
not sure. I'm just not sure I heard it right. Yeah, so yeah, can you take a look at question number part A here?
okay.
Y'all, okay.
So you do 3 times 8 first because multiplication is before addition and subtraction, which is 3 times 8 is 24, and then 6 plus 24 is 30.
Good. All right. Part B, Andy, let's take a look here. Andy, hello, you here?
Sorry, he is in the dentist's office. He
Okay.
cannot answer the question.
Yeah, no worries,
Sorry.
guys. No worries. All right, part B then. Cindy, we'll just move down the list here.
So you add 6 plus 3 first, since it's in the parentheses.
So that takes priority, right? So then what does that get you?
It gets you 9, and then 9 times 8 is 72.
Good, good, good. All right, moving on, part C. So for this question here, I'll do this one. So for this question here, we want to do the exponent first, because that exponent takes priority before multiplication and subtraction. So we do 3 squared, which is 9, times 2, which is 18. Then we have 17 minus 18, which gets you -1. Okay. All right, part D. Daniel? Oh. Okay. Daniel, you here? Maybe not. All right, Isabella.
Uh, 19.
So how did you get your answer for part D here?
Yeah, so I did.
You muted yourself.
Yeah, so I solved what was inside the parentheses, which is 6, and then 6 times 6 squared is 36. So 17 minus 36 is -19.
Good, good, good. So I think your first time I heard you say 19, not -19, but right. So -19 is the correct answer here. And yeah, you just want to take it step by step, do it in the right order, and you get your answer. All right, moving on, part E, Michael. Just talk it through step by step. You don't have to let me know just the answer. I want to hear every step here. Maybe your mic isn't working. I can't hear anything from you. If your mic isn't working, we can use the chat though. Oh yeah, that works. Typing works here. So what's the first thing that we want to do here? 2 times 3. So we do 2 times 3 first. That gets us 6. Then we have 17 minus 6 squared. So what do we do next? Yeah, so 17 minus 6 is next. And the reason why is because that's going to be inside the parentheses. So then we get 17 minus 6, that's 11 squared. And at that point, we're pretty much done. 11 squared is equal to 121. And that's exactly right. All right, thank you, Michael. And lastly here, question part F. Milo, we have a bit of a longer question here for you. Milo, hello, you there? Okay, yeah, so use the chat here as well. So what's the first thing that we're going to want to do here? -15 minus 3. So that's going to be a parentheses inside of parentheses. So whenever you have groups within groups like that, you'll want to do the one most on the inside. The one inside the most parentheses. That's the one that takes the most priority, right? So we do this first. That gets us 12. 12 over 2 is now inside that parentheses. Okay, so what do we do next? Divided by 2, right? So now we take care of this part. So this is then equal to 6 times 3 minus 2 squared times 3 over 6. So what's our next operation going to be here? Two squared, right? So this is inside of this parentheses here, and that squaring takes priority. So then that gets you 4. Okay, what's next here? 4 times 3, right? So then we finish up what's in this parentheses here. So this gets us 6 times 3 minus 12 over 6. All right, next thing we do here. Six times 3. So 6 times 3 is going to be the first multiplication or division that we see here. So we do that. That gets us 18 minus, and then from here, I'm assuming you're going to want to do that 12 over 6, right? So then that gets you 2 for a final answer of 16. Yep, that's exactly it. So these questions here, just order of operations, pretty basic ideas. These aren't really anything too new for you. They should be things that we've all been working with for a long time at this point, right? So these ideas hopefully are not new. We're just doing a little bit of review so that we can kind of use them from now on. But from here, we then move on into examples of when this order would matter, right? So question 1.2. Josie has 14 marbles and Beth has 8. Josie counts all the marbles starting with hers and then adding on Beth's marbles. Beth counts all of her marbles by starting with hers and adding on Josie's. So Natalie, for this question here, if they both add correctly, are they going to get different results? Will they find the same number of marbles? Sorry.
Yes, because commutative property, I'm pretty sure.
Yeah, so this is what we call the commutative property of addition. Commutative property. Is there any other operation that commutative property holds for?
Multiplication, I think.
Yeah, and that's actually what we're going to see in problem 1.3, right? In this here, we see that there are 6 columns with 4 tiles each, while another way that we can think about it is 4 rows of 6 tiles each. So one way we have 6 times 4, the other way we have 4 times 6, and both of these numbers are going to end up being the same thing. This right here is an example of that commutative property, right? So yeah, and that's exactly what we're saying here. So because of the commutative property, sometimes it doesn't really matter what order we add those numbers in. As long as all we're doing is addition, it doesn't matter how we write it or what order we write it. There's actually no difference. But that doesn't necessarily hold for a couple other operations, such as subtraction. So in problem 1.4, Theodore, so for problem 1.4 part A, is this true? Is 2 minus 5 equal to 5 minus 2? It's false, right? So the left side here is going to be negative, which it's going to be less than 0, while the right side here is going to be positive, right? So this side is -3, this side right here is +3. So the difference here is that we have made one go from +3 to -3, right? And then Isabella has it right here. So it's false, true, right? And the reason why is because you can see here, this is subtraction and this is division, while here we have multiplication and addition, right? So the commutative property only holds for addition and multiplication. But one thing that we said earlier was that division and multiplication are basically the same thing. Why is it that they don't hold the same property? Well, the reason why is because when we write 8 divided by 4, we're writing 8 times 1/4, right? But when we say 4 divided by 8, we are no longer saying 1/4 times 8. We are saying 4 times 1/8. The difference here is huge, right? So because of that difference, we just have not written the same thing on either side, right? The left side here that we've written is 8 times 1/4, and the right side here that we've written is 4 times 1/8. And if we think about the same idea here, we've written 2 plus -5 and 5 plus -2, which are quite obviously not the same thing now that we've written it out this way. But when we write it out like this instead, when we write it out as an addition problem, and we make sure to keep that negative sign on the same number, right? Here we've swapped that negative sign from the 5 to the 2, right? So that's the reason why these two things do not stay equal here. All right. Okay. So moving on. And as always, if you have any questions, feel free to ask. Just either just unmute and go ahead and directly ask me, or just drop it in the chat. I'm always looking at that. All right, problem 1.5. In American football, a touchdown is worth, actually, these numbers are wrong. Touchdown's worth 6 points, but let's just say a touchdown is worth 7 points, a field goal is worth 3, and a safety is worth 2. In the first quarter of a game between the Eagles and the Cowboys, the Eagles score a field goal, then a touchdown, while the Cowboys score only a field goal. In the second quarter, the Cowboys score a touchdown and a safety, while the Eagles score only a safety. So in this example here, Yvonne, how many points does each team score in the first quarter and then the second quarter separately? Eagles scored 10 points, right? So field goal and a touchdown, that's 3 plus 7, right? So Eagles have 10. Yeah. Cowboys scored 3, right? Just the field goal. And then what about in the second quarter? Second quarter, Cowboys got 9 points, touchdown and a safety, right? 7 and 2. And Eagles got 2. And then if we add them all up, both of them have the exact same 12 points, right? So what property have we expressed here? You're not sure about that? Let's get some help. Natalie, can you help her out here? What property is this that we've shown here? If you're not sure, don't worry. Just let me know.
I'm not sure.
You're not sure? All right, Isabella?
Uh,
Sorry, Isabella.
Yeah, which question do you want me to answer?
Yeah, so what property have we shown in this question here? These both teams have 12 points each. So what property have we kind of shown?
I think it's the identity property.
The identity property? Not so sure about that one. The identity property says that everything is, I think it's, I'm not exactly sure which one it is actually. It's either the one that says everything is equal to itself, but I think that's actually called reflexive. You might be thinking of something else. You might be misnaming it actually. I think the identity property is used for something much later along the lines of math. So right. So well, we'll actually throw it out there to anyone. So if anyone thinks that they've got the answer to this one, feel free to raise your hand, but I'll give you all a little bit of a clue here. So what if we thought of each quarter as a grouping, right? So first we're grouping together. I mean, if we look at the scores that each team has, right? Eagles have 1 field goal, 1 touchdown, 1 safety. Cowboys have 1 field goal, 1 touchdown, 1 safety. So they each have 1 of each, right? They've just grouped it in different ways. We've done touchdown plus safety plus field goal. In one case, this is the Cowboys, right? I've listed it as the second quarter, then first quarter. And then in the other one, we have touchdown plus field goal plus safety. So does this ring a bell for anyone here? Does this look like?
Associative property.
Yeah, that's exactly it. So this is what we call the associative property of addition, right? So if, for example, we were able to say that for commutative property, we have A plus B equals B plus A, then the associative property says instead that A plus B plus C, if we group it like this, is the same thing as A plus B plus C. So this here changes the order, this here changes the groupings. It changes the order in which we do the addition, right? So we do the addition of one over the other, for example. So that's really just all that's going on here. But if we combine between the two, it basically says that we can go ahead and add numbers in any order we want. We can add together numbers as long as that order makes it nicer for us, right? Like as it makes it easier for us to do. And we may think, well, this looks very similar to the commutative property. Why? Because it also holds this same thing, this same associative property also holds for multiplication. We can see here in this example, if we have 3 times 4 equals 12 boxes in the top layer, right? So three rows of 4 blocks each row, and there are 5 layers of that, we can say that there's 12 times 5 or 60 blocks in total. But if we do the same thing with 5 rows of 4 boxes, and then 3 kind of layers of that this way, then we can say that there's 20 times 3, which is also 60. So we can see that for multiplication, the commutative property said that AB is just equal to BA, while for associative property, that's the same thing as saying AB times C is the same thing as A times BC. Now, we'll typically use a lot of different ways to write multiplications. So we can see something like X, Y. This will mean these two numbers are multiplied. We can see X and then a parentheses Y. We can see, for example, A times B, but you'll actually see this much less often now. And the reason why is because that X, that cross that you use for multiplication, that could be mistaken for an X variable, right? That could be mistaken for a variable. So that's why we no longer use that as much. You might not see it as often from here on out. However, in replacement for that, you'll see a dot like A dot B or a star like A star B like this. Typically, this is the one that you'll see in a lot of textbooks. This is the one that you'll see in a lot of homeworks typed up by students that do not have the dot sign. They use the closest thing. But either way, this will, both of those also are acceptable for multiplication signs. So there's many, many different ways to write multiplication signs. In contrast, there's only one way for addition, and there's only one way for subtraction. Division has like 2 as well. They have this one and this one. These both mean division. All right. Let's take a look at problem 1.7, part A. Okay. Alex, it looks like you're new in here, so let's throw this one over to you. Alex, you here? Okay, 102. Okay, so how did you get this number here? How did you get 102?
Sorry, I typed the wrong number.
Oh, no worries, no worries. So how do you do this? I want to hear step by step. Don't just give me the answer.
So I did 47 minus 45.
Okay,
Means
so
that there's 2 left, and then I add that to 99, which is
right,
1.
so yeah, and that ends up equaling 101, right? So the way that you did this is the right way to do this. You want to make things nicer for you. You want to make this as easy as possible, right? So what you did was you said that this minus 45, that's the same thing as plus a negative 45. And then now that it's plus, now that it's addition, I can move it wherever I want. I can do it in any order I want. So now I do 47 plus negative 45 plus 99. And now that I have this equals just 2. 2 plus 99 is a lot easier than 47 plus 99, right? So then that's how we got your answer of 101. All right, nice job. All right, part B. All right. I mean, I guess you can do that, but we want to see it step by step, right? So let's see, part B. Cindy.
So since you're adding everything together, you can drop the parentheses.
So then how does this change things?
You can switch up the order for
Right.
properly. And so you would do 613 minus 610 plus 299 minus 298.
Yep.
So you would be left with 3 plus 1, which equals 4.
That's exactly it. All right. Part C. Isabella? Yeah. You're next anyways.
So you can just cancel out both 13s and then you just get, well, since the top is 1, so it's just 64.
Yep, exactly it. And then for part C, I can go ahead and, for part D, sorry, I can go ahead and show you guys this one. The 47 here cancels out with this one here. The 23 here cancels out with this one because it's the same. 23 divided by 23, that's the same thing as just 1, right? So then all of this leaves you with just this 3 here remaining. All right, so we'll take care of that. As always, if you have any questions, feel free to let me know. But this is just a short bit of, like, as always, this first part is just a lot of review. So don't, so like it should be pretty simple, but if it's not, don't worry. We have time to get up to speed here. But all right, so question number section 1.4. Section 1.4 talks about distribution. So if we're talking about distribution, one such property that does end up being introduced is what we call the distributive property. Okay. Michael, do you know what the distributive property says? I think your mic still isn't working. Have you tried plugging it in? I don't know. Maybe you have. Maybe it just doesn't work. You're not sure. Okay. We can throw it over to someone else. Does anyone else does anyone here have an idea of what the distributive property says? Okay. If we're not sure, we can actually take a look at question 1.8. Maybe looking at this question would help us. So, Michael, question 1.8 asks us to look at the following. We have cats and dogs, 5 cats and 7 dogs. Each of these animals has 4 legs, right? So how many legs in total do the cats have? 20, right? So we just do that 4 times the 5 here to get a total of 20, right? How many legs in total do the dogs have? And 28, right? So from here, we can add together all those numbers to get a total of 48. But if we counted a different way, we could have done how many animals there were, right? How many animals are there in total? 12. And then from there, we can multiply that 12 by 4 to get a total of 48 legs, right? So either way, we would have gotten that 48. So let's kind of take a look at what we really did here. So if we combine together part A and part B, what we did was we said 5 times 4 plus 7 times 4. This is equal to 5 plus 7 times 4, right? Because part C, we did that 5 plus 7 first. Well, if we replace these numbers with variables, for example, A, B, and C, we get the following. We get A times B plus A times C is equal to, well, actually, yeah, A plus, sorry. It's a little bit hard to see exactly what numbers are which if I write it in that order. So let's say B times A plus C times A, like this, is equal to B plus C times A. Now, normally you'll actually see it in the other direction. You'll see it as, you will typically see it as A times B plus C is equal to AB plus AC. You'll see it in this direction from left to right. This is what we call the distributive property. What this means is when we have multiplication and addition put together side by side, we can actually choose what order we do this in. We can split it up. We can split it up and do 2 separate multiplications, or we can do the addition first and then just do the one multiplication. But this is very important because this process, this idea is actually 2-directional. We can go from the left side to the right, and we can go from the right side to the left. It's a lot harder for a lot of people to recognize that from the right side to the left. It's very tricky for a lot of people to do that. So let's take a look at question 1.9. All right, so this right here, this A plus B, this A times B plus C thing, that is what we call the distributive property. So this is what we were looking for earlier. All right, problem 1.9. There are 9 children in the Connor family. Their parents buy 99 goldfish and 72 angelfish. If each child receives the same total number of fish, then how many fish will each receive? All right, Milo, let's see what you've got here. Milo, you there? If you're not sure, we can just throw it over to someone else. Not seeing anything from him, so we'll just move down the list. Natalie?
So I would add 99 and 72 first, and that would get 171.
171, you said? Okay.
Yes. And then I would divide that by 9 because everybody has to have the same amount of fish or else they're all going to scream.
Right. As usual.
Yeah. And then 19 would be the answer.
So this way you do that addition first and then you divide through. It's a little bit like 171 divided by 9 is a little bit tricky, but it's not the end of the world, right? But would there have been any different way that you could have solved this? Maybe by using that distributive property that we had said? Okay, Yang Xiaowen.
You could have done 99 divided by 9 plus 72 divided by 9. And I would have got 11 plus 8, and that's 19.
Right. So here, if we do things this way, we end up working with smaller numbers. And as always, smaller numbers are always much nicer to work with, right? So this way, we do end up getting that answer, that same answer, right? That same 19. It's still right. I mean, if we do that addition first, if we do that 99 plus 72, that's still correct, but it may have just taken a little bit longer when we work on that division part, right? It's a lot easier to see that 99 divided by 9 is 11 and 72 divided by 9 is 8, right? And then from there, adding together those two numbers isn't really hard. So I'm not saying that it was wrong. I'm not saying that you I'm not saying any of that stuff, right? It's just that there could have been a faster way. There could have been an easier way to get that answer, right? And then sometimes doing something like this would actually make things a lot easier, right? This is just one such example where the difference might not be that big. But if you had, say, for example, numbers like number of feet in a mile, which is like 5,280, right? Multiplying by that big number is a little bit hard. So maybe if you if you're working with things like that, then maybe it might help if you use the distributive property there. Natalie, does that sound good to you?
Yes.
Okay, yeah. All right, moving on. So the next section talks about equations, and there's not actually any problems here, so I'm not really going to crop it out and whatever. But the big idea here is if we have two things equal to each other, then that equality holds for both sides, right? If we have an equation, that means that whatever's on the left is equal to whatever is on the right. For example, here we have 1 plus 5 plus 1 is equal to 7. But what that also means is that 7 is equal to 1 plus 5 plus 1, right? So this is actually what we like to call the symmetric property, I think. It's basically, it means that if A equals B, then B equals A, right? So this is one that symmetric property, this is what we call the symmetric property of equality, right? Let's actually write that down just in case. Symmetric property. I cannot spell to save my life. All right, so this is what we call the symmetric property. This is important because it allows us to do a lot of substitutions that in many different ways, right? So this is going to be something that we're going to want to look at here. And one thing about equality is that if we think about it as that scale, right? If we think about it as a scale where we can kind of add and subtract and whatever on both sides, then what that means is we can, as long as we add something to one side of a scale, right? Like if we have a pair of scales here, right? As long as we add something to one side, as long as we add the same thing on the other, it's still going to balance out. So, and that's actually something that is very important in algebra. If you add something to one side and you add the same thing to the other, you still have equality. As long as you, say, for example, add 3 to both sides. Let's say we originally had 4 equals 2 plus 2, right? If we add 3 to both sides, well, this is just 7 equals 7, right? So it's still the same thing. You can even multiply both sides by the same thing, right? You can multiply both sides by 2. This ends up being 14 times 14 equals 14. Right? So you can do whatever you want to one side, as long as you do it to the other as well. You're perfectly fine. Now, there is one thing that you need to be careful of, but you will not need to do this for a while. But if you square both sides, that is going to lead to some problems, because -1 squared is equal to +1. Which is equal to +1 squared. So sometimes if you square both sides, and actually not just square, if you raise to an even power, sometimes you'll end up with answers that should not have been answers because of this issue. Because then this would tell you that -1 equals +1, which is simply just not true. But we don't have to worry about this for a while. I'm just letting you know now. All right. So with that being said, let's take a look at some of the problems. Problem 1.10 and 1.11 here. Problem 1.10 says for us to consider the balance scale below and assume that all of our weight is in pounds, right? So if we switch the sides of the weights, Theodore, is this still going to balance out? Yes. So we've actually I actually kind of already mentioned this, right? So what property is this called? Do you remember the name?
Symmetric property.
Yeah, so Cindy jumped in here, but right. So this is the symmetric property. The symmetrical property of equality, right? So it still ends up being the same thing. So 1 plus 2 is equal to 3, 3 is equal to 1 plus 2, right? So if A equals B, then B equals A. Okay. Yes. Do you have a question? Sorry. Or did you want to answer?
I wanted to do the next question.
Okay, sure, go for it. Question 1.11 then.
Okay, so it says 1,5,1,2,7,2. Okay. What equation does the scale represent? 1 plus 5 plus 1 plus 2 equals 7 plus 2.
Okay. And then part B, if we add a 3-pound weight to the right and another 3-pound weight to the left, is this still going to balance out?
Yeah.
So what is this, like, what does this represent? Like, did I say anything about this earlier?
Yeah.
Yeah, so what does this represent here? There wasn't a name for it, but it was an idea that I had said.
If you add something to one side, if you do something to one side and you do the same thing to the other side, it should be equal.
Yep, and that's exactly it, right? In this case, we're adding 3 to both sides, and that still ends up equaling out, right? And then part D says that instead of doing that, we are removing a 2-pound weight. What does this represent then?
It represents subtraction.
Yeah, it represents subtraction of 2 from both sides, right?
Yeah.
And then this idea, we are still doing that same thing to both sides. We're just subtracting 2 from both sides at this point. And that means that we still have equality, right? And sorry, but what's your name actually? I'm not sure about your third character in your name, I think.
林哲仁.
Ren, was that right?
Yeah.
林哲仁, is that right?
Yeah.
Okay. Yeah, sorry about that. I'll try to remember, but I have, but like, since we're only going to meet once a week, it might be a little bit hard, but I'll try. But right, so thank you very much. And that does finish up this problem here. This is just the exact same thing that I had said earlier, right? As long as we do the same thing to both sides, where we will always stay equal, right? So the first question basically let us know that if we flip the sides, it's the same thing. If we and then the second question here, let us say that if we add or subtract to both sides, we still have the same thing, right? So moving on into the next questions here, problem 1.12 and 1.13. 1.12 says that we start with this equation of 17 minus 7 is equal to 10, right? So if we multiply both sides by 2, and from here, this is actually just 10 equals 10, right? So if we multiply both sides by 3, well, 3 times 10 is 30, and 3 times 10 is, once again, 30, right? So these two sides are still the same thing, right? It doesn't matter what number we multiplied by. It could have been 2. It could have been like any other numbers, right? Like 5, 4. It could have been any number here. We still would have gotten the same thing, right? Now, we could have some problems if we multiplied both sides by 0, because then we could have started out with something like 5 equals 4, which is clearly not true. But then if we multiply by 0, we get 0 equals 0, and all of a sudden everything works. So please don't multiply by 0. You can add by 0, that's fine. You can multiply by 1, that's perfect. That's actually really good. When I say multiply by 1, usually you're not actually multiplying by exactly 1. Usually you're multiplying by something like 4 over 4, which is equal to 1. But please, please just do not multiply by 0. But right, so part B B here shows that if we divide both sides by 2, it's just equal to 10 over 2, which is 5, right? On both sides. So this, in combination with the previous question, allows us to use all 4 regular operations: addition, subtraction, multiplication, and division for both sides. As long as we do it to both sides, we will always have the same equality. So if we have, for example, A equals B, then we also have A plus C equals B plus C, A minus C equals B minus C, A times C equals B times C, and A divided by C equals B divided by C. Now, C, for these 2 equations, we just don't want C to be 0, typically. Please do not have C equals 0 if you're multiplying or dividing here. But all right, let's move on into problem 1.13. In question 1.13, we start off by saying, let's say we multiply both sides of this equation by 20, and then multiply both sides by 8. Well, since we're multiplying both sides by 20 and then multiplying both sides by 8, we're doing the same thing to both sides, right? We're basically just multiplying both sides by 160, right? Which is the same thing as 20 times 8. So that will be true. Now, Yvonne, if we start off with this equation, do we end up with this one? And how is it related to this here? If you're not sure, or if the question's a bit vague, just let me know. You're not quite sure? Okay, so we're actually kind of out of time, so I'll go ahead and finish this up for today. But thank you nonetheless. So what goes on here is if we multiply both sides by 43, and then multiply both sides once again by 301, you'll see that this 301 and this 301 cancels out. This 43 and this 43 cancels out. And all we're left with, because 43 divided by 43 is 1, and 301 divided by 301 is 1 as well, right? Like A over A is just equal to 1, unless A equals 0. Like A cannot equal 0 because 0 divided by 0. This doesn't work. If anyone has any questions about this, you can ask Siri or whatever. She'll give you a nice story about it. But basically what this does is you're left with 73 times 301 and 43 times 511. Yvonne, does that look good to you here? Like all we did was we just multiplied both sides by both denominators. But yeah, so this idea here is actually what we call a cross product. Now, you've most possibly been taught in school to use this. Like once you have an equation like this, you can use the cross product, which would tell you 73 times 301 is equal to 511 times 43. You've possibly been taught to use this. It's also possible that you haven't, because from what I remember, we've been taught, there was actually a point where we started to teach this less and less. But this idea is just what we call the cross product. If you have an equality like this, you can go ahead and multiply, like in that cross shape, to get both sides still equal. So for example, if A over B is equal to C over D, then you have AD equals BC. But with that, that is going to be all of our time for today. We finished sections 1.1 through 1.4, and we got halfway through section 1.5. So homework is going to be sections 1.2 through 1.4. Just the section reviews on those questions. And unless you have any questions, you're all free to go. Have a good week, everyone.
Thanks.
Yeah, no problem.